We have Jmvx, multi-version execution for managed languages, and David is giving the talk.
All right, can you hear me OK? Sweet. All right, let's jump into it. I'm going to start by talking about the record replay parts of our system, and I'll loop back over to how multi-version execution connects to it, and I'll explain everything as we go. So I'm going to start by showing some code to you. This is Java code. It's going to read in or make a stream to a config file and do some work over it, process it, and attempt to do something. And I'm going to tell a tale of two perspectives, one a user, one a developer. So a user can run this program, and if they don't have a config file, they'll get an exception. And they may go and file a poorly documented bug report to the developer that says something along the lines, oh, the program crashed at startup. The developer, upon getting the bug report, will attempt to recreate the bug. And if they have a config file, the program's going to run fine. And this is going to start a feedback loop between the developer and the user, where the developer has to probe the user for more information to replicate the bug. This occurs because the developer is unaware of the computing environment that the user is using, and namely the fact that they're missing a config file. So record replay is a method that records the non-deterministic interactions your program has with the operating system. So this means the results of system calls and scheduling decisions, and generates a recording. This recording can be replayed, which will put the program in the same state by providing the same type of non-determinism to the program, and then the developer can easily replicate the bug. So this is a very useful tool for debugging. The problem is some of the known existing systems are rather slow. So RR is a state-of-the-art record replay system for Mozilla Firefox, and it can have up to 4x overhead. As a bit of a teaser, the system I'm going to talk about today, Jmvx, can keep that much slower and stay underneath 2x. And we're going to achieve this by multi-threaded record replay that is also going to tolerate some benign divergences in the management of the JVM. So let's loop multi-version execution back into this before I explain how the system works. Something to notice is record replay is offline multi-version execution. So this is kind of the diagram of how a record replay system looks, where you will create a recording from your program, and later on you'll replay it. If instead of doing this at 2 different times and sending these recordings to disk, you sent this recording to a shared memory buffer, and you split this between 2 JVMs, and you have maybe another process that's a coordinator that sets up these initial connections, what you're really looking at is not record replay. You're looking at multi-version execution. What multi-version execution buys you, if you have a follower that is a different variant, e.g. a newer version of the software you're using, as this software runs and potentially encounters errors, you may have a different variant survive the crash, and you can provide continuous service. So record replay, very good for debugging. Multi-version execution, really good for providing continued service. And these two types of systems can be implemented with the same code base because their architectures are very similar. The problem is that both of these things are difficult for VM-based languages like Java. And this is because you have to deal with VM runtimes. So the garbage collector, the just-in-time compiler, and class loading, all of these mechanisms, particularly in Java, are designed to work differently every time you run the VM. And this problem would be, it would be much simpler to do these techniques over programs if only we were able to let the VM management bypass our record replay or MVX system and interact with the operating system. And this is the high-level design behind Jmvx, where we're going to embed our record replay system inside of the bytecode. And this way, things that the JVM wants to do where it interacts with the operating system can go straight through. And we're going to focus specifically on library calls that the program makes, so things the Java developer cares about. In order for this to work, we need to understand what a non-deterministic API is. We need to know what we need to log. And we're going to be looking at methods in Java that will eventually lead to system calls. So we're going to use a little bit of bytecode instrumentation and dynamic tracing to help find these. So we're going to wrap native methods. A native method is a method you can call in Java, but the implementation is in C in the underlying JVM. So the first method is going to clear a global flag that's going to represent whether or not a system call has occurred. The method afterward is going to check if this flag is set, and if it is, log a stack trace for us to inspect so we can find the method we need to instrument. We need a mechanism to tell us if a system call occurs, and for that we're going to use strace, and we can configure strace to send the signal user2 back to the JVM. And we'll have a signal handler that, upon getting the signal, sets the flag. So using this method, we're able to identify a lot of methods that we need to provide support for. And this is how we identified all the methods in green across these 2 tables. And I'll go into how we do the bytecode instrumentation to handle these. So looking at the example for socket input stream.read, we're going to take the read method. We're going to rename it to Jmvx read. And we're going to insert a new method with the same signature. And this is going to have some code in it, jmvx.r.get, which is going to divert into the Jmvx runtime that handles the recording, replaying, or the leader/follower's execution. This .r.get is selecting the strategy. So for record replay, the recorder will call the underlying implementation to read data from a socket, log the fact that we read some data from the socket, and then return. Whereas the replayer strategy will read data from a log file, assert that this is the operation that should have occurred and that we haven't diverged, and also return. So that's how we handle all the methods that are in here in green. Let's focus in a little bit on the outliers. So I mentioned before that class loading is non-deterministic within the JVM. Every time you run it, the order classes are loaded and is going to change. So we needed to provide special support for class loading. Unfortunately, I don't have the time to go into all the details right now because I only have 15 minutes, so there's a lot more details in the paper. I want to focus a bit more on some of these methods here. All of these are required for multi-threaded program support, and this is a major reason why we're going to get speed up over RR. Everything in red was manually identified. We decided we needed to, or we realized we need to support these in order to get programs to run. The yellow block is a bit interesting because this is something that's automatically identified. To get concurrency decisions that are being made in programs, we need to look at synchronized blocks and synchronized methods. So before talking about how the bytecode for that is instrumented, I'll talk about how we enforce the concurrency decisions. So multi-threading, the ordering of events is handled by using a Lamport clock to provide a total ordering of monitor entry. And what this means is it's whenever an object is locked in Java. So here we have a diagram of a program that's running. It's got 2 threads. There are 4 events that occur that need to grab a lock. And every time one of these events occurs, it modifies a global clock and logs a copy of it. When we go to do a replay, we may see these events in a different order. In particular, event 3 is going to try and run before event 1, which is contradictory to what we saw during the recording. In this case, the logged clock that we see in thread 2's log is not going to agree with the program's global clock and is going to be delayed. And it gets delayed until eventually event 1 occurs on thread 1, and that updates the global clock to a point where event 3 can now sync and run. And this continues for the rest of the scheduling that I have on the slide. In order to provide support for this in the bytecode, what we do is we take a synchronized method and we desynchronize it. And then we're going to apply some similar tactics to what we did before, where we change the method name and we add a new method with the same signature. Some of the code that we have here is going to re-implement the synchronized logic where we're going to end up grabbing a lock, but only if the conditions for the vector clock are satisfied. Now, I mentioned before, we also provide support for multi-version execution, and a key reason why we can provide fast multi-version execution is because we use a ring buffer that is a fast shared memory queue. It's an off-heat byte buffer that we make using mmap, and it's managed with unsafe, which provides us direct memory access, which is something that you don't normally get in Java. The key point that we want to mention here is that there's no locks used in this design, so it's very fast. And I don't have a lot of time to go into this, so please check the paper if you're interested in how this is done. Something that we also need to deal with are divergences and handling them. So we have a little bit of program output here from PMD, which may be too small to read. So I'm going to highlight the fact that the divergence happens when we print how long it took the benchmark to run. We handle this in Jmvx using a divergence handler. This is a method that you write in Java that you supply to Jmvx that will get some details on when the event you expected is different or the data you expected is different. And you can write some code on how to handle that. So in this case, this is checking that we're at the end of a benchmark and then modifies what is printed at the end of the benchmark so we still get accurate timing data from our test harness. So with all that said, let's look at how Jmvx actually performs. So I'm going to go into the cost of the bytecode instrumentation, how we perform for record replay, comparing with systems RR and Chronicler, the overhead for MVX, and how well Jmvx scales, particularly by looking at what happens as we vary the number of threads and the size of the ring buffer. As a note, most of our benchmarks are from the Decapo benchmark suite. 11 out of 12 of them are, and the last benchmark is a server benchmark we picked up from another paper. A brief note, I'm going to mention 2 modes of Jmvx, sync and no sync. Sync is when we're using all of the methods in this table. All of them are instrumented. No sync is when we're avoiding the things here in red and yellow, meaning that we don't have any support for ordering multi-threaded events. And the reason we're doing this is to have a fair comparison with Chronicler when we get there, because Chronicler isn't capable of multi-threaded replay. So to evaluate the instrumentation, we use a pass-through strategy. This means as soon as we get into Jmvx, instead of worrying about doing any logging of events, we just go straight to the underlying implementation to measure the cost of diverting the execution. So for the no-sync instrumentation, we see a 2% overhead. And for the sync instrumentation, we see a 5% overhead. So we believe that's negligible. For record replay, we have good results when we compare against RR. Namely, Jmvx has 1.25x overhead versus RR's 4.33x overhead, and 1.73x overhead for replay versus RR's 4.7x overhead. Something that we also like to point out here is RR fails for 3 of the benchmarks that we wanted to run: Aurora, JME, and Jython, and Jmvx was able to successfully record and replay those. In terms of recording size, we're, for most benchmarks, on par with RR. There's a couple where we have about twice the size, particularly with H2 and Luís search. When comparing with Chronicler, we deal with our no-sync mode because, as I mentioned before, Chronicler doesn't have multi-threaded replay. Something to point out, Chronicler was not tested on the H2 server or JME benchmarks. The data that we have on this slide actually comes from Chronicler's paper rather than us running the system because it's tied to a version of OSX that we don't have, so we weren't able to reproduce any results. And as I've mentioned a couple times, Chronicler doesn't provide replay data. Something I do want to point out from this slide, well, I guess first I should go over, Jmvx does beat Chronicler in recording overhead with 1.08x overhead versus 1.14x. But another thing that this helps us stress is you really need multi-threaded replay. You can't get away with just recording the results of some of the system calls or the library calls that those are coming from, because you'll just end up diverging due to scheduling decisions that happen on a lot of these multi-threaded benchmarks. And that's why in our replay, we aren't able to replay things like FOP or H2 without the multi-threading support anyway. For MVX, we see our leader has a 1.7 or 1.47x overhead, and the follower has a 1.8x overhead. And I think I should now go into talking about the thing I'm assuming everyone's eyes shot to, and that is, why do we perform so poorly for Luís search? And this is because our vector clock is biased towards the leader, and Luís search is a benchmark with many short critical sections. And every time we have an event that attempts to run out of order, we have to delay a thread. So everything in red in the figure that I've brought back from the Lamport clock section is slow. And these delays really add up and give us poor performance on Luís search. Another test we did was we varied the size of the ring buffer for all of our benchmarks, going from 1 megabyte, 10, 100, 250, and 500 megabytes. Luís search again points out another interesting part of our development here is that if you have an improperly sized circular buffer, particularly if it's too small and the follower isn't processing events fast enough, it can actually back up the leader. And this is very important because the leader's delay is what the user experiences. The follower can lag behind, but it shouldn't lag behind too far. Finally, we did an evaluation on how does our recording speed and replay speed change as we vary the number of threads. And what this pointed out to us is that we have very poor performance for single-threaded benchmarks. Particularly H2 when run with one thread, and Jython, which is a Python interpreter in Java. When running one thread, the JVM gets to use optimized locks that vastly outperform our vector clock. So to conclude, Jmvx operates in the bytecode rather than directly on system calls, which allows us to tolerate benign divergences in the VM's runtime and focus particularly on the calls that are important to a Java developer. We're capable of supporting both record replay and multi-version execution. We use dynamic tracing in order to identify the methods we need to instrument to support a program. And we outperform R, the most popular user space record and replay tool. So the code is available on GitHub, and I encourage you to check it out if you're interested. And with that, thank you for your time.
All right, thank you. Great talk. Any questions? Yes. Yep, I think so.
Hey, thanks for the talk. You mentioned that multi-threaded replay is very important.
Yes.
So I was curious, can you guarantee that multi-threaded record and replay is both sound and deterministic, even in the presence of things like object.wait, notify all signals and conditions and things like that, where the JVM sort of can arbitrarily pick one thread to resume from a waited state and reclaim some monitors, etc.
So we were able to implement wait find. That was one of the ones that we manually said we have to go in and add some support for, and it's through this vector clock implementation we were talking about. There are cases where Jmvx will not give you guarantees. Particularly with signals, we don't do any replay over signals right now.
All right, thanks.
Hi, thanks for the talk. I was curious about your comparison to RR in particular. I guess I recall their work reporting that the overhead was maybe like less than 2x, where you're sort of seeing 4x or more. So I was just wondering if that's kind of down to just choosing different benchmarks or something else.
So the main thing with RR's extra performance is that it takes a multi-threaded program and it runs it on a single core at any given time.
Yep.
Right, so it's really, I think, just based on the fact we can run multiple threads, and a lot of these benchmarks are multi-threaded.
Yep. Okay, thanks.
Yep.
Hi, thanks for the talk. So I was wondering, like, how do you take care about the garbage collector that might be running in parallel in the JVM?
We allow it to diverge.
Okay.
So one of the things we wanted to get to is we're focusing on trying to record and replay specifically what's happening with the Java application, and seeing that the idea behind the garbage collector is to run on its own in every time you run the VM. We just let it do its job. There are cases where this can cause complications in replay, specifically if you're using weak references for memory-sensitive caches.
Yes.
In that case, we can have replays that diverge as well. So I should have mentioned that with the first question.
Okay.
So,
yeah, thank you.
good question.
You said that there was like a less than 10% overhead, like if you just doing the call a different function and then call back to the function that you actually wanted to call. Is that this might be a naive question, but is that like just measuring the additional overhead of like doing that function call?
Yeah. We're just dealing with what it takes to do this extra method call moving in the bytecode.
How do you know that it's not like inlined?
It could be because the JIT's technically running below us, and in fact, that's kind of a benefit for us.
Fair enough.
Any other question? All right, I have one question since we have some time.
Yes.
From a replay perspective, it's really cool that you can replay the schedule of threads. From a bug finding perspective, it's a little unfortunate, right? Because some bugs that I might be looking for might have to do with different schedules.
Yes.
Is there any hope from a bug finding perspective of doing something different with threads?
Ooh,
Like,
we've had some discussions on
Okay.
it, particularly if you can post-process a replay and find out different ways of doing the scheduling, like if you can rewrite the vector clock between when you do a recording and when you actually do replay to see what would happen with different schedulings. That's work that we're still thinking about doing. We haven't made much progress with it yet, but there is hope.
Okay, cool. All right, well, let's thank David one more time. Thanks.
Thank you.